Hi, everybody. We're going to be talking about an introduction to area under the curve today. And I am going to apologize for the quality of this camera because this is my old camera that I have at home. But we're going to be talking about how what we were doing with antiderivatives kind of connects with the area under the curve eventually. And to start off, kind of introducing the idea of what the area under the curve is. Basically, when they were inventing calculus, they needed to describe how basically rates of changes can accumulate over an interval that produces the idea of this total change. So Isaac Newton actually was the one that discovered the connection between the accumulation function and derivatives, which is this idea of integral calculus or integration. And this idea of integration has to do with the antiderivatives that we've been talking about. So we're not going to be talking about antiderivatives today, but just know that there is that connection there. So we're going to be talking about today what is this idea of accumulating values or accumulating over an interval. And we're going to start off with a pretty basic example by talking about driving with your cruise control on. So say you're on a road trip and you have your car on cruise control for 4 hours. So meaning you're not hitting the brakes, you're not stopping, you're not slowing down. We're just assuming that there's like this wide open highway that you are not stopping or slowing down for anything. And you're traveling at 60 miles per hour. We want to know how far have we traveled after 4 hours? Well, if we think about what the graph of this looks like, I've got my axes labeled with y-axis is speed in miles per hour, x-axis is time in hours. So we know that our speed is 60 miles per hour. And we know that we're traveling over a time period of 4 hours. So if we're traveling at a consistent speed of 60 miles per hour, that's going to mean that our graph is going to look like a horizontal line. We're not slowing, we're not speeding down. It's just this function that is constant over the 4 hours. And if I were to drop down this line here, it's not a great rectangle, but you get the idea. The distance traveled in 4 hours by a car moving at 60 miles per hour actually corresponds to the area of this rectangle. Because if you think about what's happening, we're really taking a speed of 60 miles that we're driving, or 60 miles per hour, the speed that we're driving at, and we're multiplying it by 4 hours. And if you've done any sort of like dimensional analysis in science, you'll know that these units of hours are going to cancel out, and we're really just left multiplying 60 miles times 4, which is going to give us 240, and our units are going to be miles. And if you think about it, that's exactly what this graph is showing us. We have this base length of 4 times a height of 60, and 60 times 4 gives us this 240 miles. So this distance that we're traveling in 4 hours by a car moving at 60 miles per hour actually is corresponding to the area of this rectangle. Or, in other words, the area under the curve or the area under this function that we just drew. So we'll look at a couple of other examples, but when we talk about this idea as of area under the curve, we don't really just mean the area under or below the curve. It actually really is specifically talking about the area that's between the x-axis and the function. So there's a couple different kind of ways that you might see this represented in graphs. For example, this function is all above the x-axis, so the area under the curve would be the area, again, between the x-axis and the curve. So we'd be talking about all that area there. This curve here is all under the x-axis, so the area under the curve would actually be the area that's above the curve but below the x-axis. So we'd be talking about this area here. We know that we're not that lucky, and we can't always just have a curve that's above or a curve that's below. Sometimes the curve might cross the x-axis, and we're actually going to have area in 2 different places. So there's actually going to be 3 chunks of area here. This area is actually going to be above the curve but below the x-axis. This area is going to be below the curve but above the x-axis. And then this area, again, is going to be above the curve, but below the x-axis. So again, that's basically the area that's trapped between the curve and the x-axis when we talk about the area under the curve. And the nice thing about this is that, again, shows the accumulation of whatever the value is over time. In the last case, it was the accumulation of the distance that we traveled over the 4 hours that we were driving. So for this example, the graph is representing the rate at which the water is leaking out of a tank. And our units are given the graph. So our y-axis is the gallons per minute. Our x-axis is the time in minutes. And we want to know how much water has leaked out of the tank after 9 minutes. So I'm looking for an accumulated amount of water that the tank is losing over this period of time of 9 minutes. So again, if I'm looking for a total accumulation, I'm really looking for the area under the curve here. And the nice thing about this curve is, and a lot of the ones that we'll kind of be looking at to begin with, is that the area under the curve is actually going to be area that we can split up into smaller shapes. So we can take this apart in chunks and really just work in chunks, meaning I like to work in rectangles, circles, half circles, triangles, whatever you can break it up into that's easy for you to calculate the area, you can definitely do that. And how you do that, it's up to you. So usually I try to break it apart into the biggest pieces just for the ease of calculating the area under the curve. So if I'm looking under the 9 minutes, I'm really looking for the area total under this curve here. So maybe we can start with kind of like a rectangle shape here. Just again, to break it into larger pieces. So area of a rectangle, base, which looks like it's going to be 6 units, times height, which is going to be 2 units. So it looks like my area of this rectangle is going to be 12 units squared, whatever our units are. Here I have a triangle. My area of a triangle is 1/2 base times height. Looks like my base is 3 here. And looks like my height is 2. So 1/2 of 6 is going to give me an area of 3. And then up here, I actually have a semicircle. So my area of a semicircle is going to be 1/2 pi r squared, because the area of a circle is pi r squared, but semicircle is going to be 1/2 of that. And it looks like my radius, if I kind of cut this into 2 equal pieces on the bottom, looks like my radius is going to be 2 here. So 1/2 pi times 2 squared is going to give me 1/2 pi times 4, which is going to give me 2 pi. So if I were to add all these areas under the curve, that should tell me the total amount of water that's leaked out of the tank after 9 minutes. So my total is going to be all 3 of these areas added up. So 12 plus 3 plus 2 pi, which should give me 15 plus 2 pi. And my units here should be gallons. And the nice thing about the dimensional analysis kind of that we talked about on the first page is that you should be able to determine what your units are going to be by looking at your units on the y-axis and actually multiplying them by the units on the x-axis. Because when we do that, our gallons per minute are multiplied by our x-axis unit, which is minutes, which are going to cancel out to give us our units of gallons. So our total amount of water that's leaked out over the first 9 minutes should be 15 plus 2 pi gallons. And for these, we'll just leave our answers as exact values. We're not going to plug those into our calculators to get approximations. So for the next one, we're actually going to have to draw this graph, it looks like. We've got ourselves some axes, but we don't have a graph. So a particle is starting at x equals 0 and moving along the x-axis with a velocity of 3t plus 2 units per second for any time that's greater than or equal to 0. We want to know how far away from its starting point the particle is at t equals 3 seconds. So what this how far away is asking us is what is its total distance from the starting point. So that's kind of like the accumulation of distance that we talked about in the first example. But what we actually need to do is we need to graph what this velocity function is going to be looking like. And it looks like our units for velocity are going to be units per second. I'll label my y-axis, so units per second. And then it looks like our x-axis is going to be time, and it looks like that time is in seconds. So I'm starting at x equals 0, and I'm graphing this function 3t plus 2. So that's going to tell me that my y-intercept is going to be at 2, and my slope from there is going to be 3, so 3 over 1. And I want to make it to 3 seconds because this is the time period that I'm worried about, is from 0 to 3 seconds. So I'm going to go up 3 to the right 1, up 3 to the right 1, and then up 3, and then to the right 1. So I'm a little bit off my graph here, but you get the idea. So maybe I can find myself a sharp edge or a straight edge here. Make this look pretty. So here's my function. And again, I'm going to kind of like drop down that vertical as I did in that first example, so I can kind of clearly see what my area under the curve is going to be. And similar to the last problem, I definitely have some shapes that I can break this up into easily. So it looks like I kind of have this nice little rectangle on the bottom. So I can calculate the area of that. My base is 3, my height is 2. So that should give me an area of 6. And then my triangle here is going to be 1/2 the base. So base is going to be 3. And then my height, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's going to give me half of 3 times 9. So half of 27 should give me an area of 13.5. And then I'm looking to, again, add these two values together to get my total distance away, or my total distance traveled. So my total distance is going to be 13.5 plus 6. And my units, again, are going to be my units per second being multiplied by my time. So if I multiply those together, units per second times seconds, seconds are going to cancel out. And I should be left with, I think, 19.5 units. So it looks like my particle is 19.5 units away from the starting point. All right, we'll look at one more example that actually has to do with squirrels. So a squirrel is starting at building A at time t is equal to 0, and we are traveling along a straight wire connected to building B. For the time between 0 and 18 seconds, the squirrel's velocity is modeled by this piecewise linear function defined by the graph below. So something important to note is that this is a velocity graph. So something quick to kind of observe that's different about this graph than the last graph is now we have some of the graph that's above the x-axis, and then we also have some graph that's below the x-axis. So when we started looking at velocity graphs, when we were starting to talk about, velocity, acceleration, position functions, remember that when the velocity function is above the x-axis, that's actually telling us that our object is moving in a positive direction or moving to the right. And vice versa, if we are actually below the x-axis, our particle or whatever, our object is actually moving in a negative direction or moving to the left. So we're going to be needing to remember this for the questions that we're going to answer about this graph. Okay, so we're asking at what times in the interval does the squirrel change direction? And we need to give a reason for this. So if we are changing direction and we know that above the x-axis we're moving to the right, but then when we fall below the x-axis we're moving to the left, that must mean that where we're changing directions is going to be where we're actually crossing the x-axis, because if we're moving to the right and then suddenly moving to the left, we must have changed directions here, and then here if we're moving to the left and then suddenly moving to the right, we must have changed directions here. So we can say the squirrel changes directions, and it looks like that's going to be at t is equal to 9 and t is equal to 15 seconds. And that's because our velocity is actually 0 there. And this is since our v of t equals 0. And we know that at the points where v of t equals 0, we're either changing direction from negative to positive or positive to negative, meaning that we're going to be moving either from the right to the left or from the left to the right. So then we're asked, at what time in this interval is the squirrel farthest from building A? So if I'm asking for where the squirrel is farthest from building A, I want to know about where the squirrel is accumulating the most distance. So I'm looking for the accumulation of the greatest distance of the squirrel. So that really means that I'm really looking for what the area under the curve is, because I want to figure out where is my squirrel farthest from building A. So it looks like the chunks that I'm wanting to split this up into are actually defined for me in the graph, because I know that my squirrel is going to be changing directions, either moving from positive to negative or right to left, and then from left to right. So I'm going to look for my area under the curve as these chunks. So this big chunk up top, this little chunk kind of down below, and then this little chunk up top here. And the nice thing about this is you can do this in a number of different ways. But the easiest way I like to look at this is a trapezoid. And if you don't remember what the area of trapezoid is 1/2 times the height times base 1 plus base 2. And the bases of a trapezoid, remember, are the parallel sides. So if I'm calculating the area of this trapezoid, it's going to be 1/2. The height is going to be how tall we are here, which is going to be, it looks like a height of 20. My first base length is going to be the length of this bottom side, which looks like it's going to be 9. My top base length is going to be the length of this parallel side, which is going to be from 2 to 7. So it looks like it's going to be 5. And that looks like it's going to be half of 20 times 14. So 10 times 14 is going to give me 140. And I know that since this is above the x-axis, I'm going to be moving 140 units to the right. So I know from t is equal to 0 to t is equal to 9, I've moved 140 units to the right. So I'm going to write that down. So from t is equal to 0 to t is equal to 9, I've moved 140 units to the right, where the squirrel has. So now if I look at this middle chunk here, I've got another, again, trapezoid. Do this in a different color. So my area here is going to be 1/2 the height. And this time my height is actually negative, which is something different, kind of as what we looked at in the other graphs. When you have an area below the curve, your area is actually going to be negative, because your height, or your, whatever you're measuring here, is actually going to be negative. Looks like our height's going to be -10. And then our first base looks like it's going to be from 9 to 15, so 6 units. Second base is going to be from 10 to 14, so 4 units. So 1/2 of -10 times 10, looks like it's going to be -50, which means that we're actually moving left 50 units. So from 9 to 15, I'm just going to kind of add to my list here. From 9 to 15, we're moving 50 units left. And then I can go back up to my kind of last piece here. And again, my last piece is above the curve, so it's going to be positive area. And you can do one of two things here. If you kind of look to see, could split this into a triangle and then a square. This is actually another trapezoid if you wanted to use the trapezoid formula. If it's easier for you to divide it up into triangles and squares, that's fine. My triangle is going to have a base of, I think, 1, 15 to 16, and then a height of 10. So it looks like it's going to be 5. And then my square has a base of 2 and a height of 10. I guess that's not a square then. So that's going to give me 20. So this total area under here would be 25. And that's from 15 to 18. So from 15 to 18, I'm moving 25 units to the, again, if we're above, we're moving to the right. So at what time are we farthest from building A? So at what time have we accumulated the most rightmost distance? Well, it looks like that'd probably be at 9. Because if I think about what kind of my position is, if I'm moving 40 to the right, but then I'm turning back around and moving 50 to the left, I've gone 90 units. And then if I turn back around and go 25 to the right, I've moved 115 units. So looks like at t is equal to 9, it looks like that's where I'm farthest away from building A. So we are farthest from building A at t is equal to 9. And we can say that the squirrel is 140 units from building A at this time, assuming that building A is where we're starting at t is equal to 0. So that's where we've accumulated the most kind of positive distance, would be at t is equal to 9. So then I'm looking to see, well, what is my total distance that my squirrel is traveling? So if I'm looking for total distance, it doesn't matter which direction that we're traveling in, whether we're moving right or left. Because if I think about this, like I were to say that I travel 140 miles to school, but then once I get to school, I go, turn around and I travel 50 miles backwards in the direction of home. I'm still traveling 50 units or 50 miles. I'm just going in a different direction. And then I turn around and I'm, drive 25 more miles towards the school. My total distance is actually going to be kind of almost the absolute value of the area under the curve, because I know that I'm going 140 units to the right, but then I'm going 50 units to the left. So I want to make sure that I'm accounting for the kind of absolute value of that, since I'm still going 50 units. And then plus 25. So that should give me, let's see, what's that? 90 plus 25. I'm sorry, 190 plus 25. So 215. So my total distance that my squirrels traveled during this time would be 215 units. All right, so it's going to be your turn to do some practice. Let me know if you have any questions, and I will see you guys tomorrow.